All right, hello and welcome. In this video, we're going to look back at this RL series circuit, but this time we're going to look at the theta and the phi. That's going to be the phase angle and the phase lead, right? And so to figure out how to say some of those Greek letters, you can actually find them in Microsoft Word. In Microsoft Word, you can go up to the Insert tab, Symbol, Equation, and then in this dropdown that it gives you for opening up that equation, you can open up this basic math section and you can highlight and hover over these, and they'll give you the names of the Greek symbols that we're using. Here is the phi, and here is another one that we use, tau. And so if you ever need those, you can look them up there. We are going to do our phase angle first, and then that allows us to measure out our period for our time difference. And with these two together, we'll be able to actually calculate that phase angle. Right, so the first thing we need to do is connect our meters. We need to do the channel A across our resistor. So we'll connect channel A positive side to the top of the resistor, channel A negative side to the bottom of the resistor. That gives us the voltage drop across that resistor. We'll take channel B, we'll measure across our source voltage. If we click out here, it'll allow us to keep that bend in the wire. We can click at the front of our source voltage there, and then at the very bottom, the ground location, and that can be anywhere on the bottom ground. Right. So let's change the color of our voltage source by right-clicking in segment color there. We can change it to like a green color so we can tell the difference here. We'll OK that out. Now we have our voltage source off the front. Measuring around there, we can compare those two, our voltage to our linear resistance, right? Because if we were to measure across our inductor and our resistor and compare the voltage drops between those two, we should find that they're 90 degrees apart because the linear resistor is 0-degree phase and the inductor is 90-degree phase. We'll find capacitors at negative 90-degree phase, right? So now that we have this set up, we can measure our period on our oscilloscope. So let's double click on the oscilloscope and we'll hit play on that. And we'll move backwards just a little bit so we can see our signal. And this is currently tracing that red wire, right? And we actually want to trace the green wire. And so we can double click on the green one and go backwards here, and we can see now it's tracing that green one. And if you can't double click on it, you can select right click, select trace, and select channel B there, and that will do the same thing. So the first probe line, we want to right click and go to next Y max. That's at the top here. The second probe line, we want to do the same thing. We want to go right click next to next Y max. We just want to make sure that they're on separate peaks, two different peaks that are kind of side by side right here. We're looking to find the time interval it takes us to do one full cycle rotation. That's called our period. And so we see that right here, one full cycle back up to the very top peak. That's one time. And so our T2 minus T1 should be our period. We see that right here, microseconds, 100 microseconds. So we're going to write that down as our period value. Our period is equal to 100 microseconds. Right? Remember, our time is on this horizontal axis. So now we need our difference in time. The difference in time is the difference between these two waveforms. So let's leave the blue one completely alone. It's at the top peak of that waveform, so we don't want to touch it. Well, actually, let's send it down to 0. Let's send it down to 0. Let's move this down to this 0 axis line here. So if we right click and go to the previous Y value of, just put a 0 in there, that's going to put it all the way down to that axis. And this is a more accurate calculation or measurement that we have here. And we can check our period here to see if it's as accurate as we need it to be by doing the same thing. Let's go back down to the next Y0 axis line. And that sends us back down to this bottom. We see it's still microseconds, right? If we didn't do this for this next measurement, when we switch over to the other meter line here, it ends up getting us an inaccurate reading. So let's right click, select trace, and we'll go to channel A. That's our resistor. We don't want to touch the first probe line here. It's right at that 0 axis of the previous signal. But we do want to move this other one to be really, really close so that we can get it to this 0 crossing line. So we'll right click that and tell it to go backwards to the next Y, and we'll set 0 in there also. We should see that both of those are crossing at where the green crosses the 0 line and where the red crosses the 0 line. And that gives us this value right here. So we'll set this equal to 16.456 microseconds. So now that we have this, we can calculate our measured phase angle. And so that is a calculation after we have done some measurements. Now that we've got our two time factors, we can say, but let's compare them. Let's put them into a ratio of total time versus time interval in between these two phases here. And that's going to allow us to compare angles of our circle. Right? So let's say that that would be our change in time divided by our time factor total, that's our period, multiplied by the number of angles we have in our circle, which is 360. Right, so that's going to give us the full rotation of that circle cycle and all the angles that it has with it. So let's do that. We'll plug that in. We'll say that we have the change in time. That's that 16.45. We'll divide that by that 100 microseconds. They're both in microseconds, so it's going to cancel out. Then we'll multiply that by 360 degrees. 59.22. That's also in degrees, so make sure your calculator, I guess this one doesn't matter. The next one will. So this one is equal to our phase angle, that's our theta, and it's 59. We can round that off even and just say it is in degrees there. So now we have our calculated angle, and that's the other one. That's that tangent equation. And so we can solve for that one by saying that we have our theta is equal to the inverse tangent, tan to the -1 of our xl divided by our resistor, right? The nonlinear on the bottom, the nonlinear on top, the linear on the bottom there. So let's send this out and we'll calculate that. Because we know those two values, we just got to figure out what our xl is again. Let's exit out of this one. We know that our resistor is 6,000 and our inductor is 160 millihenries, but that's not ohms, right? That's not XL. So we have to convert that. We have to figure out what XL is, and that's that 2 pi FL equation. So we'll say 2 pi times our frequency, which is 10,000, so 10,000, multiplied by our inductor value, which is 0.16. Move it all the way down to henries. Let's go 0.16. Right, and that gives us, we'll round that up, that gives us 10,000, right? 10,000 or 10 kilo ohms. And so we can plug that in for XL and use that in our R equation. So we'll send this out and we'll say that we have the inverse tangent equation and we want our XL on top. So we can say that the previous answer we just had goes on top, and we'll divide that by our resistor, which we know is 6,000. Right, that gives us 59.2. Right, we can round that up, but we can round it all the way down to 59. So now we know that they match, right? Equals 59 degrees, right? So they should match. So if yours do not match, make sure that you have measured the correct side. Make sure you've gone down to that 0 axis line. Okay, so that was everything we needed to know about our resistor. So let's get rid of some of this stuff here. And we know that our measured phase angle was 59 and our theta value here was also 59. So we can write that up here out of the way a little bit. And we can use similar process for the other one. So let's do that next. We need to move our meters here because we just measured across the resistor compared to the input source, right? And that's going to be the difference between those two phases. But now we need to change from the resistor to the inductor so that we can measure the phase lead, right? Not the phase angle. The phase angle is the difference between the source and the linear resistance. The phase lead is the difference between the source and the nonlinear resistance, like the inductor and a capacitor. So we're going to grab this meter line here. We're going to move it in front of the inductor, and then we'll move the other side of it to the back side of this inductor, anywhere on that line there. It's still red. It was red before, so now we just got to know that that's the inductor line. And if you want to, you can swap that over to what we were using for the inductor color before. Make it more obvious that that's still the inductor there. Our input line is green here, and so we get to compare those two. We're going to do the same period, and we're going to compare the phase difference between the two, and then we're going to use that to do our measured phase angle. That's a little bit different when we go to calculate it. So let's hit play on this, and we'll double click on our oscilloscope, and we'll compare those two signals here. Stop that and move it back. They look a lot closer, and check out the green one is actually in front of the blue one, right? That's what we're talking about when we're saying that it's leading. The blue one came in first even though it was an inductor, which means that we're seeing that flyback voltage a little bit. So let's right click and go to the next Y max. I double clicked on my green signal. You can also, again, right click trace and go to channel B on that. I want this blue one to be up front, so let's move this one forward again and we'll put that to the next Y max, and we'll put this one in the front position here to the next Y max. We see that we have the same period, right? The period did not change between these two because we never changed the frequency, right? The frequency didn't change, the period didn't change. So 100 microseconds is what we expected for that. The next one is our difference between these two signals. Let's go in here and right click and select trace. We'll switch back to channel A and okay that. Then we'll move this one all the way back here, and then we'll tell it to go down to the 0 axis line. So go down to 0. okay that, and we'll move this other one. Oh, we got to right click, go back over to that other channel. We didn't move it down to 0 before that. So now we don't want to move channel 2, but we can move channel 1 here. And this actually shows something interesting with our time interval too. So we'll go backwards down to 0. And that's going to move us right back down. And we see that that's right next to each other. We do see a negative time interval, but that's just because I have the T1 on the other side of T2. Right? And it kind of shows us what this phase angle means as well. It means that that inductor has pushed something backwards, right? The voltage across the inductor showed up before the actual source voltage. And that's what we're seeing there as well. So this is not a negative time value. Time cannot be negative. But this is an 8.54 microseconds. Right? So now we can do our same time interval value where we put the change in time on top. We'll put our change in time divided by our time value multiplied by the rotation of our circle, which is 360 degrees. And we'll send that out. So we'll evaluate this here and say that we have the change in time. They're both in microseconds. We'll leave that off. 8.54 divided by 100. 100. And we'll multiply that by 360. 30.7. Right? So we can round that up to 31. 31 degrees. And that is our measured phase angle. So we can do the calculated phase angle. It's similar to what we did before. We did the phi before we did our theta, right? Let's write the theta up top. The theta was equal to our inverse tangent of our linear component on bottom, our nonlinear component on top, right? And that gave us the information about that resistor. So we're going to do the opposite down here. We're going to say that our phi is equal to the tangent equation, inverse tan, of our linear component on top, our non-linear component on bottom, right? And that focuses on that inductor. Instead, that gives us this phi symbol, right? Like just like we measured, or we changed our meter connections there for the same reason. Okay, so let's send this out and we'll do the same thing. We know our XL did not change. It's still the same frequency, so we should find that that's still right about 10,000 ohms. And so we can just plug those in and we'll say that our inverse tangent equation first, we'll put our resistor on top, 6,000, and divide that by our inductor value, which was 10,000. And we'll say that we have 30. We'll round that up, 31 degrees. There we go. So they match. They should match. Okay, so now we want to make our phasor diagrams. So we're going to do 2 of them. We're going to do one for just the resistances, and then we're going to do another one that is just for our voltage. So to do this, we can right-click out here and place a graphic. We can do a multi-line, and that multi-line allows us to drag and drop lines down. So we can do a perfectly vertical line on one line here. Click once, and it'll let us do another line. Click again, and we'll drag that all the way back up to the start line and double-click, and that'll give us an entire triangle there. That's what we want for our impedance phasor. So then we can right-click and place text. And we want to place a text for each one of these. We know that the upper rise is going to be our XL, so we can even put that in up here, XL for now. We also know that we have another one, so we'll right-click, place graphic and text, and we'll go on the bottom one. This is going to be our linear resistance, our R value. Right? We could do that one more time, right-click, place graphic, text, and this line here is going to be our Z. Right? It's our middle magnitude of the two. And we also have our phasor impedance angle in between those, and that's actually going to be between our R and our Z down here. And so we can place another one, right-click, place graphic, and we'll put it in a text box down here, and that's actually going to be our theta. Oops. Right, that's our middle one there. And we know what that is because we've just found that, right? So we know that we can type in 59 in there. So we'll replace that here. You can even say that it equals 59 degrees. And that is for that inner angle down there at the bottom. The resistor value we know, so we can double click on that. And we can say that this is equal to 6,000, 6K. Right? That sends us there, and it is in ohms. We can type in ohms, or we can go and copy ohm value from one of our other variables. This other one up here, this XL variable, we know what that one is as well. We calculated that out a couple of times. That's equal to 10K ohms. Put that one in up there. And then we just need our Z variable value. And we remember that one was 11.79 from before. And so you do have that one above if needed. Equals 11.97 volts. About that. 79, I believe, actually. Backwards. not volts, ohms, right? That's our ohmic value. There we go. We got to do one more though. We want to do one that shows off what is happening with our voltage at both of those locations as well. So that one's a little bit different, but we can do the same thing. We're going to right click and we're going to place graphic. We'll do our multi-line again. This time we'll do the same rise. We'll click once to stop that there and go over. We'll click double right there. And then we just need one more line here. We need to set something in the middle. So we'll right click and place a line. And we'll start at the bottom corner of our square or triangle that we have started here, and we'll put out right in the center there. And that will be our line. So this is going to be our actual voltage that we have. Right, so let's grab a couple of these. We'll copy one of these and we'll paste it so that we can have something to paste a text box with. That gets us our text box out. Make sure your circuit's off if you're trying to paste or copy things in your zones. So this one's going to be our voltage, V in, our V out voltage there. Our voltage across our inductor, so let's copy and paste this one, is going to be up here, VL. Right, we'll copy and paste that one down here again, and this is going to be our VR, which means that this one up here in the middle is going to be our VZ, right? It's going to be the Z magnitude voltage, the voltage across both. And what they really want us to do here is figure out where our theta is and where our angle is, theta, and our phase lead, our phi. And so we know that this was our theta here. We'll copy and paste that down. That was on the resistor side, right? So we'll put that on the resistor side of our phasor diagram. And we can copy and paste that one again and put it up here on the other side. But it's not called theta this time. It's called phi. And it's not equal to 59. It's equal to 31. Right? And so we'll put that in at the upper one. And you might even be able to rotate that sideways if you wanted it upright there, so that you can show that it's a part of that inductor line there. Okay. That is what we wanted from those. Let us know if you have any other questions.